Alright, so I want to do the same problem again, but this time I'm going to use more of a traditional approach. Okay, so first step first step's identical. All I do for the first step, let me move this guy right here, that's a lot better. Okay, so the first step is just a force diagram. So here's my system. I have to choose a system first. Okay, that's a little hard to see. Maybe I'll make that red. So there's my system. Okay, it's the block, and I got the weight, and I got normal force. And my system is going to represent it as a dot. Okay, that's a pretty big dot. Maybe I can make that a little bit smaller. I don't know. How's that look? There we go. And this is the weight of the object, and this is the normal force. So this is identical to how we did it before. But now what I'm going to do is I'm going to sketch reference lines. So I'm going to define X and Y directions. So, and I like to put an arrow on the side that's positive. So this I'm going to call positive Y direction, okay? And then my perpendicular to that will be my positive X direction, okay? And this is going to be the direction of my acceleration. So I'll say this is positive X direction, okay? And I should draw some more reference lines so that I can clearly identify the 40-degree angle of the ramp on my force diagram. And just like before, you will notice that every other angle on a tilted ramp will be the same 40-degree angle. Okay, so I just need to be careful here to identify my angle correctly. This is 40 degrees, right, from my picture. This angle here is that angle there. And you'll notice that that's the same as this angle here. And normal force will also tilt the same amount, so that's that angle there. And this angle right there is actually the same. Okay? And again, the only forces I have are my normal, which is that one, which I'm just darkening in a little bit, and my weight, which is straight down. So those are my two forces. Now, the same approach works for multiple force diagrams, multiple forces. The same approach is pretty reliable. It doesn't involve a lot of creativity, and it's very reliable, but it's a little bit tedious and the logic's a little confusing. Okay, so I define my x and y, my xy directions. Okay, so you notice that the weight vector does not lie on either of those directions. Okay, so let me redraw my weight vector. It's down. Okay, that's my weight. Now, this vector, the weight is made up of two vectors. My weight in the parallel to the y-axis and the weight parallel to my x. So these are the x and y components of the weight. And these vectors, this is a 90-degree triangle, right triangle, okay? Anytime you add component vectors, components by definition will be at right angles to each other because one component is in the x direction, one is in the y direction. And you'll notice that my component vectors, wx vector, that looks like a y, plus wy vector, add to give me my weight vector. Now, what that means is I can actually replace my weight with my components. So instead of drawing the weight on my force diagram, I'm going to do a new force diagram, okay? And I'll just do it over here to the right. I'll do the same exact coordinate system. I'm not going to mess with that. I'm not going to change that. And you notice my up, down directions are not defined x, y. You just define your x, y in whatever way is convenient, and you make sure that your acceleration is either in the positive x or the positive y direction. That's pretty important. Okay, and then you're going to use Newton's laws in the x direction and Newton's laws in the y direction separately. Okay, so now I'm going to draw my perpendicular to surface y direction. Okay, and you want to draw your xy direction in such a way that as many vectors as possible are captured on your initial force diagram. That reduces the amount of work, and it reduces the chances of making a silly error. So now I'm just redrawing all my reference lines exactly as they were before. There's my x direction, my positive x direction, and you note that that is the direction of my acceleration in this case. So now I'm going to add my vectors, right? And I'm going to draw my normal force exactly as it was. I'm going to still draw a dot for my system, and there's my normal, okay? My normal force is like at an angle in the y, positive y direction. I'll label that normal. And what I see now is my block is not going to have any acceleration in the y direction at all. I know that because the block can't go through the floor, right? So the block's not going to have acceleration in the y direction. So what's going to occur is my wy vector, my y component of the weight, should be the same exact length as my normal force, right? And I should probably figure out my xy components too. If I look carefully here, this angle right there is my 40-degree angle. It's a little hard to see there, so I'm gonna redraw it a little bit different. I'll just draw a little angle guy, and I'll say that that is the same angle exactly as that one there, right? Because it's the same little triangle that you're looking at. All right, so that means that Wx is going to be W sine 40 degrees. And that means that you can say that Wx is actually mg sine 40 degrees. And Wy, now if you find that part confusing, you might want to go back a step and just say, well, sine 40 degrees is going to be Wx over W. That would be a first step. And if I find cosine 40 degrees, cosine 40 degrees is going to be Wy, the y component of the weight, over W. So that means Wy is going to be weight times cosine 40 degrees, or another way of saying that is Wy is going to be mg cosine 40 degrees, right? And the other component, the Wx, is going to be the component that's responsible for my acceleration, W, in the x direction, right? And I'm just copying it. I'm copying this vector and this vector, right? And I'm not drawing my weight. I'm replacing the weight on my axis-only force diagram. That's what this is, axis-only force diagram. And that's showing all the forces only on my x and y directions, all right? And this was my original force diagram over here. And then I would just apply Newton's laws, right? In the y direction, the sum of the forces in the y direction equals 0, since acceleration in the y direction equals 0, right? And my forces in the y direction, well, I have normal in the positive direction. I have wy in the negative direction. Sorry, there's a negative there. And those have to add to 0, right? Because they're in opposite directions and because there's no acceleration. Okay, so the normal has to equal wy, which is mg cosine 40 degrees. And this is exactly what we got before. And I would simply do the same thing in the x direction. Okay, so you're going to find that in the x direction, what we have is sum of the forces in the x direction equals, well, it's not going to equal 0 because I have a net force in the x direction. It's going to equal ma, right? In the x direction. The only acceleration is exactly in that x direction, and that's why I had to make my positive x direction my direction of my block's acceleration. So if I want to find the acceleration of the block in the x direction, I'm going to have to take my net force and divide by the mass of the block. That is my net force in the x direction. All right, and you'll recall that my net force in the x direction should be just wx. So it's going to be wx over m, right? And what's wx? Well, wx is mg sine 40 degrees divided by m. You notice m divided by m is 1. So I get the same thing. I get acceleration in the x direction is equal to g sine 40 degrees. So you can see it's a bit more complicated doing this the traditional way, but that took 12 minutes. Wow. The logic's a little more confusing and involves a lot more steps, and you could imagine how much worse it gets as you have more and more vectors and you have multiple systems where you have to draw a force diagram. You just have a lot more work here. But it is a nice method that does work well once you understand what's going on. Anyway, I hope it helps, and have a good day.